Well, hello everyone. This part of our group project is going to be a video part, and then we'll dive into the computational theory of the mind, or CTM. I plan to look at what CTM is, how it got started, what it has accomplished, and what the major issues are against it. CTM is a philosophical concept holding that the brain is an extremely complex symbol manipulation device which computes inputs from the natural world to create outputs in the form of further mental or physical states. Basically, the computer is seen somewhat as a computer. Not so much a computer that sits on your desk, but in this case a very specific computer, which was described by Alan Turing, therefore called a Turing Machine. Here's a description of a Turing Machine given by Mr. Turing himself. An infinite memory capacity obtained in the form of an infinite tape marked out into squares, on each of which a symbol could be printed. At any moment, there is one symbol in the machine. It is called the scanned symbol. The machine can alter the scanned symbol, and its behavior is in part determined by that symbol, but the symbols on the tape elsewhere do not affect the behavior of the machine. However, the tape can be moved back and forth through the machine, this being one of the elementary operations of the machine. Any symbol on the tape may therefore eventually have an inning. Turing, 1948, page 61. At the heart of CTM is the idea that thoughts are a form of computation, and a computation is the process of taking input and following a step-by-step algorithm to get a specific output. This view requires representation, because input has to be represented in some symbolic form. Since it is impossible for the brain to compute an actual table or any other physical object, it has to have a symbol of some sort to represent the table. The interpreted table, combined with symbols for what is happening with the table, and symbols for the mental state of the observer, all have to combine to give an output in symbols, which then has to be translated to physical action by the observer. The symbols in the mind are part of the language of thought, or lot. By combining the symbols in specific ways, following certain rules, many new meanings can be given to them, just as the words of our everyday language can be combined in many ways to construct sentences, with a possibly unlimited amount of meanings. According to CTM, humans think in an inner language known as mentalese, by manipulating symbols. According to one of the main proponents, and sometimes called the founding father of CTM, Jerry Allen Fodor, symbol manipulation is what lies behind all forms of human intelligence. A frequent catchphrase often seen in connection to classical CTM is that the mind is to the brain what the program is to the hardware. Although it's an elegant and easy to understand analogy, it does expose the theory to a world of criticisms and possible flaws. One famous argument against the computational theory of mind comes from John R. Searle and is called the Chinese room argument. Picture a man in a totally isolated room. There's no way of communicating to anyone or anything outside of the room except for a piece of paper with Chinese symbol on it that is passed underneath the door. The man doesn't understand Chinese, but is told to use a series of books which tell him what Chinese symbols to use in response. For a Chinese person outside the room, this can generate a conversation which is perfectly meaningful. But does the man in the room really understand what is going on? It is of course referring to the working of our brain. We have stuff going on in the brain that gets processed in a certain way, and a response is produced, which seems to have some kind of meaning. Each part of the brain can contribute to the calculation or computation. But shouldn't there be like a little man somewhere inside who coordinates all this and produces the final meaningful output? Is it possible for a complex system like the brain to translate input into mentalese, manipulate it in a meaningful way, retranslate it to real-world symbols, and provide a meaningful output which it fully understands? Even one of the main proponents of CTM, Jerry Fodor, argues that the theory can explain the modular processes, but that it will fail to explain what he calls the central system. With a central system, he means that part of the brain where modalities are integrated, where deliberation occurs and behavior is planned. This idea ties in with the Homunculus Argument. This argument is often used as a fallacy when explaining vision. When light hits our retina, what is actually seeing the images that get formed at the back of our eyes? Is there a little man inside observing it? We call that also the Cartesian theater. In more general terms on how the brain observes every input, we can ask the same question. Who or what does the observing of incoming signals? And who or what makes decisions on what needs to be done with those inputs? By supposing recursive decomposition, CTM proponents try to explain it away. They state that there is a multiple level of homunculus within any system, so that at the lowest level of there is a basic homunculus doing very simple yes-no or 1-0 type computations. The problem is that there's always that last homunculus that cannot be explained away, the central system. There are more arguments against CTM for which a solution has not yet been found, but it doesn't mean that it's not a viable theory. More recent theories are making modifications to the classical theory of computation to address these issues. A promising approach is the connectionist version. The proponents of this theory accept a lot of the same theoretical framework as the classical version, but they differ in how the brain deals with the incoming information. They propose neural networks as an alternative. Neural networks consist of interconnected set of nodes and describe mental states and memory as changing numerical values of activation and strength of connections over time. It is not clear yet which theory, or if any, will best describe the workings of our brain, but these are some of the promising prospects. It is interesting to see how closely related CTM is to both cognitive science psychology and artificial intelligence. Cognitive science psychology is the effort to understand intelligence. It embraces philosophy, psychology, artificial intelligence, neuroscience, linguistics, and even anthropology. The ancient Greek, and probably cultures before them, already tried to understand and explain the mind. But it wasn't until the 19th century, when experimental psychology made its debut, that our effort escaped the realm of philosophy. Several years of progress were lost when behaviorism dominated the psychology arena because they were not interested in what was going on inside the black box. But the invention of computers helped spark a new interest in the process behind the scenes. Artificial intelligence became a new field of study and was quickly adopted by the field of psychology to produce new theories. CTM is a direct result of this new direction in research. At the moment, these three fields are so intertwined that they stimulate each other. CTM research opens new possibilities for artificial intelligence researchers to pursue, and of course new ideas of actual computing in the computer industry also open doors to new theories for both CTM and the more general cognitive science field. In my mind, it seems likely that at some point in the future we will be able to at least mimic the functions of our brain. The fact that we are currently struggling to make our computers do the complicated things that our brain can do is no reason to assume that we will not be able to in the future. This fallacy of ignorance might melt away as we gain more knowledge of the brain and of computer programming. This does not necessarily mean that we will have duplicated our brain. It merely means that we will have copied the output that comes out of the black box, which is our brain. Like all models that science creates, it's an approximation of the real world. It is the best representation we have at that moment of a particular phenomenon. Any new data or more accurate measurements can always require us to modify or completely change the model. That is what science is all about. Thank you for your attention and enjoy the rest of our presentation.